Hey, Phoebe, good morning.
Sorry. Am I the only? I'm not the only senior in this class.
No, I think there should be seven of you.
Like Nava and Jordan. Yeah.
Six or seven. It's weird to walk into the building this morning and see other human beings, other teenagers. It's really weird. It's like usually I only see you folks on a screen, and today you were real. I mean, still, they're just 11th graders, but good
I
morning,
feel like
Nala.
sending.
In fact, I couldn't even work in the classroom this morning. I'm in the science office. I've you know, been sent out, but once again, I'm all by myself. No other adults, no other human beings. It's very weird. Sophie and Jalen, Isaac, good morning. All the seniors are here. While the juniors take a meaningless test in the midst of a viral pandemic. Sorry, I'm not a big fan of standardized tests.
We aren't either.
It's good to hear. Oh man, I forget. Morning, Zach. All right, go ahead and log on to those Pear Deck slides. We're going to want them for today. Only got four of the seven of you, so take a moment and pop onto those slides. Sorry, I'm just working from my laptop this morning. Usually I have two screens going, so I'm doing the best I can. But I'll still do everything I usually do, monitor the chat, all that good stuff. All right. Well, good morning.
Good morning.
Thank you, Isaac. I appreciate that. Obviously going to be a strange dynamic today, just being the eight of us, but the seven of you. But I did want to try to get some work done, some learning accomplished, especially because our next lab write-up that isn't due until next week. You've got a full week to work on it. Is an opportunity for you to explore, albeit virtually, um, honeybee behavior. And I want to show you today how you could go about analyzing the data that comes out of that virtual lab experiment. And I don't know how long it will take. So my hope is, we'll be able to get through this in about half of the time together, and then I'll give you the other half of the class to either work independently from me or work with me on any of those other assignments, whether it's still lab number 5 or corrections to summative assessment number 2, or even getting a jump start on summative assessment number 3, which is not due until next week either. I think that's Monday. It should give us time to still work together collaboratively, if that would be helpful to you. Okay. What questions do you have before we get started this morning?
I don't have any.
All right. It's good to see your faces. As I was sharing with, I think Phoebe got in here first this morning. I was sharing with the PSAT happening today in the building. It's like the first time this year where I've actually seen teenagers in the high school. And I even recognized some of you. Not you, of course, because you're not here today, but I recognize some of the people in class. So it was nice to know that you're not just figments or pixels. Maybe it would be a better way to describe it on a screen. You're actually real people. So with that in mind, let me minimize this real quick here. I still think it's important to treat you like human beings. And even though there's only a few of you here today, the check-in for today, we've seen it before, but this one's going to be a little bit different. Again, you should see two icons this time, kind of a red place mark and then a green triangle. So the task is simple, much like it was the other day. With the red place mark, use that to show where you were feeling yesterday or how you were feeling yesterday along this continuum. And then use the green triangle to show where you are today, how you're feeling today. So kind of a before and after rather than just a right now approach. Looks like everybody has responded. All right. So what do you see as you look at this? What are you noticing?
People didn't really feel well yesterday.
Yeah, with there only being 7 of you, right? Maybe the results are a little bit more pronounced.
Quite possibly.
Yeah. How about those green triangles? What might they be suggesting today?
Mood generally improves because this is like the pre-Friday.
Ah, interesting. The pre-Friday. You're true. It's true. Without there being school on Friday, right? At least not for you. I have school. Yeah, it's kind of like a Thursday, right? We're almost done. Long weekend coming up. Yeah. As I look at this, what I'm reminded of is this one constant that exists in life, even in really uncertain times like these. The one constant that I keep coming back to is change. Change is the constant, right? But change is hard, right? We like there to be routine. We like there to be certainty. We like life to be somewhat predictable. And yet, when I look at this and what you shared this morning, and I really appreciate your willingness to share how you were feeling and how you're feeling right now, it's that even when we think about just a day ago and how we were feeling, how we're feeling today is different. That we don't get stuck necessarily. Although some people might be, and that's okay. The capacity, the possibility for change always exists. So even in those darkest days where things don't seem to be going well, maybe it's just possible that things could get a little bit better if we just allow for some time to elapse. So thank you for sharing. Oh, one more person just popped in. Clearly did not want to do the check-in. Welcome, Nick.
Hey, sorry.
Okay.
A little bit late.
Glad you're here. Glad you're here. All right. So, for everybody, what I mentioned at the beginning of class is that on, what is today? Wednesday. So on Monday, we looked at animal behavior, right, as an example of a characteristic that might exist within a particular population, within a particular species, that natural selection may have influenced over the course of time, right? By now, my hope is you've watched the animal behavior Edpuzzle video and you've had a chance to explore both the proximate causes, the how of different behaviors, and the ultimate causes of these behaviors, the ultimate causes being the why. And for the why, we can often come back to natural selection as the why, right? That whatever the behavior is and however it works, right, more than likely it's increasing the chances of survival and or the chances to reproduce within that particular population, within that particular species. That's why it's favored. And we also highlighted briefly the notion that if you're an individual that does not possess those characteristics, right, because natural variation is an intrinsic component, right? So that's an intrinsic characteristic of all living systems, that if you can't perform the behavior or you're not responsive to the behavior or you don't know that the behavior exists, you probably will have been selected against. So with that in mind, what we want to do today is begin to explore the possibility that when we look at these behaviors, when we kind of break them down and dissect them, we can look to see whether or not different relationships exist within different aspects of the behavior. And I'll give you some examples of those relationships here in a second. But I wanted to share this slide with you first because this slide is going to kind of give you a framework for where we're going to be going today. So it starts up here. Let me get my pen out so I can draw a little bit. It starts up here with this number 1, all right? So we've already done a little bit of this work in class already. We just haven't looked at it through this particular framework. So with this chart, what we're going to begin to do today is ask a really fundamental question. What type of data are we looking at? And in this case, we're going to be looking at animal behavior data. And data really comes in 2 forms. It comes in discrete forms or categorical forms, and then continuous forms. And you are far more familiar with continuous forms of data. So for me, continuous data is anything that exists along a continuum. So anything that involves tracking a particular measurement over the course of time would be something classified as continuous data. So any change that accumulates, that decreases, that we can measure over the course of time is continuous. Discrete data is different. Categorical data is different. It's like we're counting the number of events that are taking place. And in fact, we're not going to use the chi-square test today. So we're not going to follow the red. We're going to follow the green today, at least partially. And we'll come back and circle back to the chi-square test next week. So our focus today is going to be on continuous data, and data collected over time, which when you think about animal behavior makes sense, right? We want to watch what animals are doing, what plants are doing, what fungi are doing over the course of time. And then what we're going to do is ask a statistical question, right? In many ways, we're going to pose a hypothesis. We're going to spend some time here in a second highlighting the different types of hypotheses that you might test. You might even have some familiarity with these types of hypotheses from other classes. If we were to keep following the green arrow, you've done a little bit of this work already with, is there a difference between the means, right? We've been doing that by plotting error bars and asking the question, do the error bars overlap? And if they do, well, there isn't a significant difference between the means. And if they don't overlap, then there is a significant difference. There are other ways that those data can be analyzed. We're not going to do that today. So today, what we're really going to do is follow the purple arrows, all right? So after we have that question, what we're going to follow up on is ask ourselves the next question in series and say, okay, given what we're exploring, right? Given the fact that the data that we're collecting is continuous, right? That it's being collected across time, is there a relationship between the 2 variables that we're interested in? And to do that, we're going to explore this linear regression test as the means to the end to answer the question, is there a statistically significant relationship between the 2 variables that we're interested in? All right. So let me just pause there for a second. Is any of this bringing questions to mind? Curious, have you seen any of this before in other classes? Like in chemistry, have you done linear regression analysis, or in physics?
maybe in physics, but it's been years and I can't remember that well.
For sure, for sure.
Also, you should start calling on people.
You think so?
Yeah, maybe. I'd get them to talk a little bit more.
I hear you. Some people smirked when you said that, Isaac. I don't know if you saw while you were speaking. They're like, I don't know if it's a really good idea. It's a good thing that Isaac is living in his own house right now, so I can't come over and knock on his door. My hope is that you're growing more and more comfortable in this uncomfortable setting to share your thinking, even if that means just posting in the chat, right? That's totally okay. It's totally okay. I want to honor the fact that some people are introverts. I'm actually an introvert, and that this is really hard for me to do, right? To bring myself into this space and to be honest and transparent and forthright. So if you're more comfortable posting something in the chat, please feel free to do so. All right. So maybe you've seen some of this, but maybe you haven't. And if you have, it's been a while, so it's probably worth spending a little bit of time and reviewing it. But it sounds like it might be new for a lot of you. All right. So what types of relationships might we be exploring? Well, if we come back to the animal behavior example from Monday, maybe we're interested in asking the question, is there a relationship between something as simple as the length of the waggle dance? Remember that free run that the bee made that kind of was pointing in the direction of the food source, versus the distance that actually exists between the hive and the food source, right? We might wonder, okay, well, is that just like a random distance that the bee is following, or is it actually communicating a particular distance to other bees? Now, we know that that's what the bee is doing, but as scientists, we want to demonstrate, we want to provide evidence in support of that particular relationship. But we could go on, right? We might ask questions like, is there a relationship between the frequency at which the bee is vibrating, right, and the quality of the food source? We really didn't even think about that on Monday, right? Great, there's food over there, but is it any good? Is it worth actually flying towards? We might begin to ask questions like, the angle of incidence, right, from the hive relative to the sun to the food source versus the time of day. There's all these different possibilities. And then I even thought about other things that have nothing to do with animal behavior at all. I was kind of brainstorming last night for myself, but we might ask questions about the relationship between the infectivity rate of coronavirus and UV exposure. You might say to yourself, why would there be any relationship between UV exposure and how likely you are to be infected by coronavirus? Well, there's evidence coming out that the level of circulating vitamin D in your bloodstream might actually serve as a protective mechanism against coronavirus infection. And what we know is that as you move closer and closer and closer to the equator, where UV exposure is most intense, vitamin D levels in those human beings are at their highest, right? So we might begin to ask simple questions like that, right? And there's other examples here that we don't need to belabor. But ultimately, those are the sorts of things that we're going to try to address with these linear regression analyses, right? Here's where it's going to probably be different for a lot of you. The way that we do this in science is, and I've challenged some of you on this in your lab write-ups, and maybe even out loud from time to time. It's this tendency to use the word proof or even proven when we talk about our data, or even when we talk about making scientific claims. It's really, really important to note that those words, proof and proven, have no place in scientific analysis. We can't do it. It's impossible, okay? And one of the reasons why we can't do it is because of that pesky natural variation within populations. There's always the possibility that what we're looking at is being influenced by natural variation and not by the variable that we're actually exploring. All right. So what we're going to do instead, and it's going to be weird, but kind of ride with me here if you can, is what we're actually going to begin with is not a hypothesis to analyze, but a null hypothesis to analyze. That doesn't mean the hypotheses that you've written for this class or even in other classes are invalid. We're just going to look at the analysis of our data through a different lens. And we're going to start with a null hypothesis. And luckily, they're really simple to define. In short, what a null hypothesis is telling us is that there's no relationship between the variables that we're investigating, right? So I put some different bullet points here that I don't need to read. You're welcome to read them on your own. But in short, the null hypothesis is a simple statement, and it simply says that there is no relationship between the variables that we're exploring, all right? And down below, what I wrote was another way to think about this is that when you describe the null hypothesis, what in essence you're saying is that whatever it is that you've measured, whatever it is that you've observed, right, compared to what you would have expected to take place on its own, are the same. And if there are any differences between what you're seeing and what you would have expected, the null hypothesis is confirming that those differences are due to chance. For us, are due to natural variation within the population that you're investigating, and not because the variables themselves are different. All right? So in that last bullet point, I wrote that the independent variable does not have an effect on the dependent variable in a statistically significant manner. So if we find ourselves supporting the null hypothesis, what in effect we are saying is that the independent variable does not have an effect on the dependent variable, and any variation that we're seeing is due to natural variation, is due to chance. All right? So let me pause there again. What questions is this bringing up? This is weird. This is a different way of thinking about analysis and data analysis. Now let me ask you this then. In the chat, could you paraphrase your own definition of a null hypothesis? So working with what you've got right now, if you were to take a moment and reflect, what does the term null hypothesis mean to you right now? What is your definition? Just go ahead and type it in the chat. And if you're unsure, you can make it a private message to me, or you can write it to everybody. Who's gonna press enter first? You're just trying to paraphrase or develop your own working definition for the null hypothesis. Thank you, Isaac. Number one. Thank you, Phoebe. I like that. Ooh, I like that, Zach. Randomness. Nice. Thank you, Jordan Cole. Thank you. Uh-oh. Who did we just lose? They'll come back, I bet. Only got 4 of you, and there's 7 of you. Oh, thank you, Sophie. This phone never rings. That's really weird. I'm not answering it right now. That was my science office phone. That's weird. Nice. Thank you, Jalen. Nice. Yeah. All right. Nice. Good. Good. So you're getting the idea. So here's what we're going to try to do with these null hypotheses, right? You've all paraphrased your own definitions, and they're wonderful, right? That there's no relationship between the variables that we're testing, right, or that we're investigating. Right? That there's no effect of the independent variable on the dependent variable. That if there are any differences, right, then those differences are due to chance. I love Zach's term of randomness or natural variation within the population, right? They're all wonderful ways to explore this. Here's what we're going to try to do with these null hypotheses. We're going to try to disprove them. Because if we can disprove that there is not a relationship between two variables, what we're actually lending support for is an alternative hypothesis, that there is a relationship between the variables, right? That the independent variable does affect the dependent variable, and that it affects the dependent variable in a way that rises above the level of chance, of natural variation. I'll use Zach's term one more time, of randomness. All right? We're still not proving anything, right? We're not providing proof. We're only providing evidence, but we're providing evidence in support of the alternative hypothesis, the hypothesis that there is a difference between the variables, that there is a relationship between the variables, by disproving the null hypothesis that there is not a relationship. And this is what scientists do all of the time. They're not really collecting data in support of hypotheses. They're actually collecting data so as to refute, dismiss, invalidate null hypotheses. So let me pause there one more time. Questions? The quicker, so if you're interested in pursuing a major in science, I know some of you are from your previous contributions. If you're interested in a career in science or medicine, the faster you can let go of the notion of proof and proven in respect to trying to support a hypothesis, right, and making a scientific claim, the better off you're going to be, right? Because there's no such thing. We can't prove anything scientifically. And as you're going to see as we come back from our break, we're still going to take a break today, right? The way that we actually reject or dismiss the null hypothesis will still not completely eliminate the possibility of chance, of natural variation, of randomness from influencing the outcome of what we are comparing.
So if it's like math, you can prove it because it's a law, but if it's science, you can't prove it because of the nature of science.
I like that. It's a great way to paraphrase it, Isaac. Thank you for sharing that. Yes.
So does that global warming is mathematical or scientific?
Well, I think there's certainly mathematical measurements that are being made in support of the climate changing both locally, regionally, and globally, right? What ends up happening is that climate change denialists come in and they'll say things like, well, you've got all this data, and 99.7% of scientists agree that climate change is happening, but what about those 0.3%? What about those people that are arguing that everything that we're experiencing is just the outcome of random change, of natural variation in the climate? And the problem is that most lay people, right, most non-scientists, they've never been exposed to the idea that you're being exposed today to today in class, right? That there's always natural variation. We can't eliminate natural variation, randomness, chance from the equation entirely. That doesn't invalidate our arguments, right? Our arguments are still being supported with vast amounts of data and statistical analysis. But if you're going to cling to the 0.3%, I can't stop you from doing that.
Okay, then.
All right. So let's take a short break. I've got 9:28 on my watch. We'll come back together at 9:31 and we'll start working with these ideas a little bit more. Okay? I'll see you in a couple minutes. Get up, move your bodies. All right, if you could start making your way back. Right. So let's practice with this a little bit. And we'll begin our practice with an example from animal behavior. All right. In fact, this is an example that I derived from one of the possible variables that you might explore in lab number 6. So give yourself a moment to read the scenario. It's not very long. You can look at the data if you'd like. And then when you're ready, write a null hypothesis that you think would work for this investigation in the box. In fact, if you'd like, if it would be helpful, I can put you into student mode. So that if you want to go back and look at the definition, or the definitions, I suppose, you can certainly do that. It's like we've got three responses so far. Try to add your null hypothesis. We'll be able to look at them all and evaluate them here in a moment. About halfway, 5 of 8. Well done. What might be a null hypothesis for this exploration, this investigation? Is there a relationship between these variables? See how you're doing. All right, hopefully you can see the responses from your end. Can you see them? So you can see the responses. Can you scroll up and down to look at the different responses? You can't? Okay. So I can do that part for you. I won't go too fast here. Here, let's do this. Let's take you out of student mode here real quick. Yeah. Yeah. Nice. I'm hoping you're seeing what I'm seeing. I'm just going to try to scroll slowly here so you can get a sense of what everybody is writing. No relationship, no correlation, does not affect. Yeah. All right. Be careful offering another reason why the relationship doesn't exist. With a null hypothesis, you can keep it very simple. It's just a statement that there is no relationship, no correlation, no effect. We don't need to go to the level of explaining or offering a reason why um, the difference doesn't exist, or even does exist for that matter. Okay? All right. You're getting it. This is great. All right. So once you pose that null hypothesis, how do you go about testing it? Because again, what we're trying to do, if we can, is to disprove, to invalidate that null hypothesis, right? If we can disprove a statement where we're saying that there is not a relationship, we're providing evidence, not proof, but providing evidence that there is a relationship. Okay. So here's how we're going to go about doing that. All right. We're going to go ahead and calculate a new statistic, one that you might have some familiarity with from another class, but maybe not. It's the R value. The R is often just shorthand for the correlation coefficient. And it's a way to measure how strongly two variables are related to one another. Okay. So let me show you quickly how we go about calculating R. In fact, we're never actually even going to need to calculate it. We're going to have Google Sheets calculate it for us. Noticing that my link is not doing what I want it to do. So I'm going to jump out of here real quick and change what I'm showing you. Stop sharing for a second. And I'm going to do a new share here. Sorry if I'm jumping around a little bit. All right. Hope you can see this okay. The sheet's still working. All right. Can you at least see the data on your end in the table? It's the same data in the table that was on the slide a moment ago. All right. All right. So they're the same measurements. Okay. And all I've done is taken those measurements and plotted them on a set of axes. Now I have done a scatter plot rather than a line graph or a bar chart, anything like that. That's going to be important because it's going to be the easiest way to see whether or not there's a relationship between the data. All right. So I plotted that data and I actually made a video that will show you how to do this in more detail for lab number 6. But just quickly, all I've done here, and I'm hoping you can see this on your end, is used that chart to draw a best fit line through the data points. And this is something that at least your physics teachers have told me you did back in 9th grade when you looked for relationships between distance and time and velocity and time and things like that, right? So what's nice about Google Sheets is that it'll draw the trend line for you. It will allow you, if you so desire, to plot the equation of that best fit line. And it will also give you the correlation coefficient, or at least the squared value of the correlation coefficient by default, right? So in this case, that value is 0.417, but the value that we're going to use in our analysis is simply the square root of R squared. It's R. So R is the correlation coefficient. And in this case, the square root of 0.417 is 0.646. So that's the value that we're going to use in our analysis. Right? So let me pause there again. What questions is this bringing up, if anything at all? Have you done things like this in the past, like drawing best fit lines through data points? Thumbs up, thumbs down. Yes, no. Have you calculated correlation coefficients for those best fit lines before? Yes, no. Nice. Okay, good. This is familiar. That's awesome. That's awesome. And if it's not, that's okay too. All right. So really, this is the only information that I need is that R value at 0.646. So I'm going to go ahead and switch screens here again. Sorry to cause so much. With only one screen, it's a little hard to have two things up at the same time. There we go. Link. All right. So here's how we're going to use that, that value, 0.646. All right. So we've got that R value. We didn't have to calculate it. It's coming directly from Google Sheets. If that value is less than a critical value, and that value will always be provided to you. You do not need to memorize it. I'll in fact show you the table here in just a second that has those values. Then what we're going to have to do, right, if the value that we've calculated, if R is less than the critical value, then we're going to have to accept the null hypothesis. Because what that's telling us, if the R value that we calculate is less than the critical value, is that indeed there is no significant difference between the variables. There's no relationship. And any relationship that we think exists is due to chance, to natural variation within the system, to, I'm going to still use Zach's term, I love it, to randomness. But if the opposite is true, if the value that we calculate is greater than the critical value, we're going to be able to reject the null hypothesis. We're going to be able to support the alternative hypothesis that there is a significant difference between those variables, that the independent variable has an effect on the dependent variable, that there's actually something happening here that is not due to chance or natural variation. Okay? And everything that we're doing here, it's important to note, is a way to look at a relationship. Somebody used the term correlation in their null hypothesis. That's a really good use of the term correlation, that there is not a correlation. Correlation is not the same as causation. We're not saying, even if we get to a point where there's a correlation coefficient of 1, right, a perfect linear relationship between the variables that we're investigating, even if that is the case, we are not saying that this independent variable is causing a change in the dependent variable. We're simply making the argument that there is a relationship, a strong relationship, right? But not a causative relationship. Instead, it's a correlative relationship. There's something going on between these two variables in such a way that they are related to one another. Okay. All right. So your next task, I'm going to actually show you how to do this before you get a chance to write on it, is to actually do that analysis. So if you remember, the value for R was 0.646. Okay. So here is a table of these critical R values. The table is not hard to use, okay? But there's, oh my gosh, there's two pieces of information that we're going to need to be able to use this table effectively, okay? And the first one are the degrees of freedom. And the definition of degrees of freedom in many ways is outside the scope of this class. We're really just using it to do our analysis. If you ever really want to know what degrees of freedom are, I can spend some time with you either during learning support or after class today, kind of breaking it down, unpacking it. But really the derivation of degrees of freedom is not super important to us. We're just using it. For this analysis, the way that we're going to do it is we're simply going to look at the number of pairs of measurements that we're comparing and subtract 2, right? Really 1 for each member of the pair. So if we go back a step, how many pairs of measurements are there in this analysis? Say it out loud. You can put it in the chat. Who got in there first? Let's see. Yes, thank you, Isaac. There's 9 pairs. So with 9 pairs, how many degrees of freedom are we going to work with in this analysis? Remember, it's pairs minus 2. Isaac first in. Nope, Zach's first in this time. 7. Nice. The math is super complex, right? 9 minus 2. All right, so we're going to scroll down to 7 degrees of freedom. We're going to move over. Oh gosh, this is a horrible critical value. Sign of the beast, 0.666, right? But that is our critical value, all right? So the question becomes, is 0.666 greater than or less than our calculated R value? Do you remember that R value? Wasn't it 0.634? Sounds about right. So our calculated value is less than the critical value. So what we're going to have to do, if we go back a step, is accept that null hypothesis, that there is not a significant difference between the variables, and anything that we're seeing is due to chance. So in essence, we're not going to be able to conclude, at least using these data, that there is a relationship between foraging time and nectar collected. Right? Just because the bee spends more time looking for nectar doesn't mean that it's going to collect more nectar. Maybe you're even noticing that in the data, right? That there was an increase and then all of a sudden it began to plateau. And heck, maybe you're even wondering why. Well, so would a scientist, right? So would a biologist. Heck, maybe we're even going to argue, well, come on, there's a finite quantity of nectar that a bee can actually collect. Go ahead and forage for an infinite amount of time. Eventually, your belly's going to get full, right? It begins to make sense that there is not a relationship, right? Or at least a strong relationship between foraging time and nectar collected when you begin to think about the different variables in play that might limit the strength of that relationship. All right. I'm going to come back to you here real quick. How are we doing? You ready to try one on your own before you go? Thumbs up, thumbs down. Okay. It's different, but it's important. All right, so here's what I'll do. I think you've got just enough time to try one on your own. I'll put you back into student mode. And what you're going to want to do is click through to one of the practice problems. It doesn't really matter which one you do. I think there's 3 of them after the bee foraging problem, but the same parts exist. Read the scenario, write your null hypothesis. Okay. This time around, you actually should be able to click on the data table and it will take you to the spreadsheet automatically. So you don't have to plot the data or have Sheets calculate the R value at all. It's all going to be there for you. Just see if you can do the analysis, right? Describe the relationship and support whether or not that relationship exists using the data. All right. You've got just enough time to do those 2 parts. And I'm here for support. People are going for the death, anxiety, and religiosity question. Maybe it's the first one that you saw. Maybe it's catching your interest. It doesn't really matter. I already love what I'm seeing. Not a correlation, no correlation. Do not have a significant correlation. I love it. Wonderful. Wonderful, wonderful. So again, you're in student mode so you can see all the information that we've tried to go over. Use that to your advantage. And you should be able to click right on that data table and it will bring you to the spreadsheet so that you can see the R value. Again, the goal there is to support it with evidence. So is the calculated R value coming from the spreadsheet greater than or less than the critical value at a particular number of degrees of freedom? And if the value that you calculate is greater, Well, that's nice. You get to reject the null hypothesis. But if the value that you calculate for R is less than the critical value, even a little bit less, it doesn't matter by how much, you're going to have to support the null hypothesis. And I already love what's popping out already with people who are adding their thoughts. Please try to use the evidence. It's great that you're restating the null hypothesis, right? In many ways by describing the relationship, but support that description with evidence. I'm seeing that pop up as well. It's great. Yes, yes. You folks are getting it. This is great. This is not easy stuff, by the way. Students around the country struggle with this. Remember, make sure you're using the value for R and not R squared. The critical values in that table are all referencing R and not R squared. If you're looking for an answer, you can find the answer in the Unit 4 notes. Unfortunately, I can't flash the answers up here quickly. He's not with Pear Deck. But it's got all of the values and justification for whether or not we have to support or reject that null hypothesis. So as you wrap up those descriptions, I always want to honor the time. I'm going to fast forward here a little bit. I'm going to take you out of student mode.
So then,
And before you go, if you could just drag your dot. As you think about what we did today, how much more practice do you think you need? And as soon as you've dragged your dot, you are welcome to sign off.
Have a good day, Mr. Bergeron.
Take care.
Thank you.
Welcome. Sorry, I guess I can take this off. Mr. Verby was in here, so.